And using the sigmoid function on top of the linear combination of the original input, where we can sort of build a schematic of the classifier in this way. So you have input comes in, and this is n+1 variable including the bias. And since your input is 1 plus m, so you have 1 plus m weight vector. And you're going to aggregate the weighted sum, and we are going to call them as C. And this C goes into the logistic function. So eventually you have the outcome. And this outcome represents the probability of being decision 1 given the observation x. So this G1 is going to give you some value between 0 and 1 based on input x. And each time you're going to get some probabilistic value. So if something is close to 1, 0.99, 0.98, then it's going to be somewhere around here. So you can determine the class membership of the observation watch 1. Well, sometimes you're going to get the outcome probability 0.01 or 0.02, something like that. Then you can say the outcome label is 0. So based on the probabilistic value, where this is just a heuristic, but oftentimes you can make a decision based on probability 0.5. So if the probability is larger than 0.5, it's going to be class 1. Probability is smaller than 0.5, it's going to be class 0. So this whole thing is explaining the process of approximation. So we are approximating the binary decision y using the sigmoid function. So we can rewrite things in this way. Y is 1 over 1 plus e to the minus wtx. And if you play with this quantity, you can easily come up with this equation. So wtx is representing log of y over 1 minus y. So the idea here is we use weighted sum of x to represent this quantity. And what is this quantity for? So that's going to be our question. So y over 1 minus y is equal to OG. Not the exact translation, but OG means chance. And we put log in front of it. So well, simply this is equal to log OG or log. So the name logistic regression comes from logic. So we want to model a logic of binary decision. So this binary decision is indicated with y. We want to represent this decision in terms of weighted sum of x. Besides what the name represents for, logistic regression models the probabilistic function f that is coming from x and goes to a value between 1 and 0. So the value is again the probability of decision. And from now on, we want to build some function that is representing this probability. And since we are modeling probability of something being 1, 1 minus that probability is the complementary probability. So probability of y being 0 can be also calculated. And once you have a function that does this, where based on the heuristic decision rule, so any probability larger than 0.5, where you can make a decision based on that, where that is summarized over here. So if probability of y being 1 is larger than half, then you can make a decision where y is 1. So logistic regression defines the same decision boundary. So when G1 is larger than half, it's going to be class 1, and the outcome is smaller than half, then it's going to be class 0. And so where the sigmoid wx is equal to 0.5, that's going to define your decision boundary. And decision boundary can be obtained from the calculation as well. So we are talking about two different discriminant functions from the beginning. So we have G1 at hand. So that is sigmoid wtx. We also can obtain G0 by 1 minus sigmoid wtx. And we want to find the position where those two quantities are equated. That means we put log in front of it. where log 1 is 0. So where g1 and g0 value is the same. So we can start from this equation, log g0 over g1. We can expand it in this way. So log of a bunch of exponential and 1 plus something. Well, these two are equated, so they are gone. And these two simply become exponential negative WTX. So eventually you have log of exponential negative WTX. And these two cancels out. So eventually you have negative WTX is 0. So let's go back to the previous slide. Although we fit with the sigmoid function, this sigmoid WTX equal to half, that is equivalent to WTX is 0. So we talked about the representation of the model and the behavior of the model as well. We talked about the decision boundary of the logistic regression. Now let's talk about the training process of the model. So training goes with the data set. Actually, this should be small d and superscript n. So you have n is ranging between 1 to n. So you have capital N different sample. And for each of the instances indexed with small n, we can define this probability. So based on what we have discussed, so this is defining some probabilistic value computed with sigmoid function. And let's call this probabilistic value using mu. And since this is a probabilistic value coming from the sigmoid function, we can also write down this notation. And on the other hand, where like we discussed, p of y equals 0 can be computed using p of y equals 1. So they are complementary relations, so we can simply say 1 minus mu superscript n. And that is again equivalent to 1 minus sigmoid c. Well, next step we want to write down is the likelihood function. So likelihood and setting the log likelihood and set the derivative to 0, that's the way you get the gradient value. So starting from the likelihood function, we want to get the probability quantity of your observation. And you can rewrite things in this way because we have probability mu and the actual observation y. So actually this follows the Bernoulli distribution. So based on the probability mass function, we can simply write down the likelihood function in this way. And what we need in the next step is log likelihood. So there are reasons why we need log likelihood. Well, simply putting log in front of the likelihood value, we can obtain this notation. So the summation of y multiplied by log mu, 1 minus y multiplied by log 1 minus mu. And based on that log likelihood function, you can obtain the derivative in this way. So where if you do partial derivative on each value of w, so indexed by j, wj, you can obtain x multiplied by y minus the probability that you estimated. So if you look at the value over here, where the quantity inside of the parentheses, this represents the error in prediction. And this error is multiplied by your observation. So this is the result of a partial derivative, and you can write down the total derivative in this way as well. So things are represented in terms of a vector. Well, if you are curious about the derivation process, I have written down all the expansion and computation process over here. So slide page 40, where you can read through the entire derivation process. But where if you cannot follow, well, it's still okay. Well, now we have a derivative value at hand. Well, based on that, we can write down this gradient descent updating rule. The reason why I wrote down gradient ascent, well, this is log probability, and log probability is monotonically increasing. and we want larger likelihood. So we want to increase the log likelihood. So this is the original goal. But the optimization tool that we have is a gradient descent. To achieve our objective in logistic regression, we simply put a negative sign in front of the goal. Specifically, we put negative 1 over n in front of the log likelihood that we obtained. So instead of going up, we can still go down and we can apply the same algorithm that we have. So gradient descent with this modified j function that can be written down in this way. And you can further expand it like this by taking the partial derivative with respect to w. So this is how you obtain the vector w that is building a logistic regression model.